Okay, in the last video, we looked at the end on going over the review reactions of forming enamines and Schiff bases. So we took the secondary amine and reacted it with a ketone to form a laser pointer here. Where's my laser pointer? We took the secondary amine, reacted it with a ketone to make the enamine, and we took the primary amine and reacted it with a ketone to form the Schiff base, or if this R group is a hydrogen, which means that it came from NH3, then that's technically the imine. So that was with the primary amine. And in this chapter, what we do is we can combine that reaction with using something like hydrogen and palladium to do a reduction. And so if you do that, what you end up with is the amine. So if you take the enamine and reduce it with hydrogen and palladium, you'll reduce the carbon-carbon double bond by adding two hydrogens to it, so you can make that tertiary amine. And if you were to react the Schiff base or the imine with H2 and palladium, you're going to reduce the carbon-nitrogen double bond to form in this case, a secondary amine. Now, you could also use lithium aluminum hydride for the second reaction, but let's talk about what we ended up with. So, another reaction is called reductive amination. So in this case, what you do is you take your secondary amine and react it with the ketone, and you form then sort of what I called this compound the hemi-aminal. And instead of reacting this with heat, if you do this at room temperature and then add acid and heat to it, the acid has to come after the reaction has gone forward, because remember, the acid, if the acid was present at the beginning, the acid would have reacted with that nitrogen. So we then add acid and heat, and what happens is we protonate the OH, so water leaves. We form this compound that has two resonance structures, and then if we use hydride as our reducing reagent, we can go ahead and reduce that down to the amine. And so the effective result is that we've made an amine by adding basically in this case adding a tertiary amine, and in this case we have a problem. Let us forget about, I can't erase this. I did this wrong last time. Forget about this last step. This is the correct product. So we'll talk about how this happens in a moment. Okay, so once we get to this point where we've lost our water and we form these two resonance structures, then we can add an H- to this, and the H- will then make the final amine, and there shouldn't be hydrogen. There shouldn't be a hydrogen there. So we're going to talk about this mechanism along with the other reaction of using a cyanide group in making the nitrile. And that's going to lead us into talking about reactions that were on the last quiz that no one said, hey, those reactions aren't, we haven't talked about those reactions until after the quiz was due. So check because you're going to get a second opportunity to do that quiz, and I'm going to keep the highest score, but you can see the Canvas site for more details on that. But let's talk about the molecule that we made. So we took our amine. There's a double bond, a positive charge on the carbon. So this is the compound that we had before. That's one of the two resonance structures. So what happens is that you react this with an H minus. And the H minus typically comes from a different kind of reducing reagent. It's going to be sodium. If we go back and look at this, it's going to be sodium triboron with 3 H's and a CN. So the CN is attached to the boron to create this is going to create a milder reducing reagent. And we'll talk about the difference between strong and milder reducing reagents as we go through the reactions to form ketones. So actually I'm going to go back into chapter 22 with some reactions that aren't in there that were on the quiz. All right, so if we add an H minus, what happens? The H minus comes into the carbon, pair of electrons moves to the nitrogen. We end up with the nitrogen with a lone pair and a neutral charge, and then the hydrogen adding to the carbon. So the net result of this was that this part of the amine originally came from the secondary amine. This part, that group with its 2 R groups came from the ketone. So that is the correct mechanism for reductive amination. Now, let's go back and review the idea of using the azide as well as using the nitrile group. So last time we said that, let's say you take a primary halide and you react it with cyanide, which is C triple bond N. We can do an SN2 reaction on this so that the cyanide comes in, kicks off the chloride. We do an SN2 and we make that nitrile. Then I said that we could take lithium aluminum hydride and that would reduce the C triple bond N to a primary amine. And so we should probably talk about the mechanism by which that reaction occurs. Now, there might be a little magic involved here, but I'm going to kind of limit the amount of that quote-unquote magic and explain where it comes from. So the biggest problem here is that lithium aluminum hydride has up to 4 H minuses. So let's talk about what happens to the nitrile to completely reduce it to a CH2 NH2 group. Okay, so let me rewrite that. Now, when we react the first H minus with a nitrile group, the H minus comes in, attacks the carbon, and the pair of electrons goes to the nitrogen. So the molecule I'm going to initially make is, I'm going to add my first hydrogen. My nitrogen has now 2 lone pairs, and there's a double bond here. The nitrogen has the negative charge. Now, the lithium aluminum hydride is made up of a lithium plus and an ALH4 minus. Okay, and So when that AlH4 minus loses an H minus, it becomes a neutral AlH3. Now, the lithium is going to become the counterion to the nitrogen. But then this aluminum hydride, if you remember, aluminum is a group 3 in group 3 on the periodic table. So it actually could form a bond between the nitrogen and the aluminum. So I would end up with something that looks like this. A double bond to the nitrogen, the minus charge counterion by lithium, but then the nitrogen can also be attached to the AlH3. And that's going to be sort of one of those one of the bonds that where the nitrogen is going to take its pair of electrons and basically share it with the aluminum. Now, the aluminum hydride can then say, you know what, let's take a second H minus and have the second H minus attack that carbon. And then have the pair of electrons now from the nitrogen, or have the second double bond go to the nitrogen. Right. So if that happens, my carbon now has 2 hydrogens attached to it. My nitrogen is not in a great position because now it becomes sort of an N2 minus here. So it's got now 2 lone pairs, and it's going to be a 2 minus charge. The lithium plus would be 1 counterion. The aluminum becomes AlH2 plus. So now there's 2 counterions for that nitrogen 2 minus. And what happens now is that N2 minus isn't really a stable species. I'm done with the aluminum, the lithium aluminum hydride reaction. So when I dump water in along with acid, I'm going to protonate that N minus, the N2 minus, to form then just the primary amine. So that's not a mechanism I would ask you to reproduce, but if you're wondering how would you get the how would you completely reduce the nitrile down, that's kind of how it happens. The azide is going to do something somewhat similar. So remember that the azide, I took a primary alkyl halide, I reacted it with N3 minus. So the center nitrogen had a +1 charge. The 2 nitrogens on the end had a negative charge. The nitrogen with the negative charge comes in and does an SN2 reaction. And I end up forming then the azide that way. Now, how do we reduce this when we treat this with lithium aluminum hydride, which again is a source of 4 H minuses? How do we convert that to the final product, which is going to have a CH2 and an NH2? So we're going to reduce the azide down to an NH2 minus, or sorry, to an NH2 group. Sorry. Well, here's what happens. What happens is that there is a resonance structure you can draw for this azide. I could take this pair of electrons, move it here, and then take that pair of electrons and move it to the nitrogen. So my nitrogen would have two lone pairs. And now what that'll do is that will then keep that nitrogen with a positive charge, and then this would have a negative charge. But here's what happens. What happens is now this group right here is a good leaving group. It's actually a very good leaving group, because now if the H minus comes in, adds to this nitrogen, and the pair of electrons goes to that nitrogen, I end up forming, and again, this is a very awkward reaction, but it'll work. I end up forming an N minus, but then the I forgot a pair of electrons up there. So then we'll end up forming nitrogen gas. So this is a good leaving group, because basically that's nitrogen gas that's going to leave. Okay, so the H minus will come in and basically do like an SN2 reaction. Okay, I still have an N minus here. So when I add my H plus H2O step, like I do with all lithium aluminum hydride reactions, I'm going to end up forming the primary amine, because the H plus will be will react with the N minus. So that's how an azide basically becomes an NH2 group, through using lithium aluminum hydride. Okay, so these are both kind of awkward reactions, but they do work in terms of being able to form the final products. And the problem with azides is, what you've done is you've embedded a gas molecule, and that's a recipe for an explosion, because basically this molecule has a nitrogen gas molecule ready to form. And so by using the H minus, we basically cause that nitrogen gas to leave as a leaving group. Okay, so that kind of completes where I left off in terms of the mechanisms. But now what it does is it opens up talking about the reactions that I didn't talk about when I posted the quiz, and we need to go back and talk about other preparations of aldehydes and ketones using primarily different types of organometallic reagents. And we might as well talk about these now. You'll have the opportunity to go back and answer those questions on the quiz, and then I'll keep the highest score of the two quizzes. But let's jump into this. So, first reaction is, if you take a carboxylic acid and you react it with something like methyl lithium, which again is basically the same as methyl magnesium bromide. One equivalent of methyl magnesium bromide or methyl lithium, the CH minus is simply going to deprotonate the carbonyl, and you're going to end up with a carboxylate and methane, the CH3 with the H on it. If I then add H plus H2O to this, I didn't do anything. I ended up forming the carboxylic acid. Now, that was the so-called trick question from Grignard reactions. Grignard's one equivalent of Grignard reacted with the carboxylic acid, ended up just deprotonating it, and you reform the carboxylic acid. So that reaction we had talked about before. But now what I want to do is now I want to take my Grignard, or my organolithium compound. It's just easier to do it with an organolithium. But now, now I want to add two equivalents of that. And so the first equivalent is just going to simply deprotonate. So I'm going to end up with my carboxylate and my methane. Now, what would a second equivalent of Grignard do? A second equivalent of Grignard would actually attack the carbonyl. And we would form an O- to go with the other O-, but now I added the methyl group to the carbon. We've talked about in the past, well, maybe the O- wants to bring its pair of electrons down. Maybe this wants to come back down here, but then something's got to leave. There's nothing that can leave, so this molecule is stuck. I'm now going to add H plus H2O to it. When I do that, what do I form? What is that molecule? That is a hydrate. Now, are hydrates stable? No. Right? Hydrates weren't stable. So in the presence of H plus H2O, what happens to that hydrate? Well, one of these OHs gets protonated. Doesn't matter which one. I form that oxonium ion, and what happens next? Water leaves. And I have that carbocation. Is there a resonance structure for that carbocation? Yes. Take this pair of electrons, move it here, and I have my resonance structure. What is that? If you said that's a protonated ketone, you're correct. I'll lose my H plus. And I'll form my ketone. Okay. So, what happened? What happened was that when I took a carboxylic acid and I added two equivalents of an organolithium compound or a Grignard, it doesn't matter, but two equivalents, what did I end up forming? The ketone, where the OH has been replaced by the organolithium alkyl group. So this is technically a preparation of a ketone from a carboxylic acid. Can we understand this mechanism? Yes. Because we know about hydrates, and we know that hydrates are unstable. And if you say, well, that's a new mechanism of taking the hydrate and reacting it with the acid to form, all of these different steps, it is, but we wrote this reaction in the forward. We wrote it in the forward direction. This is the first time we've actually written it from the reverse reaction. So when you take a carboxylic acid, react with 2 equivalents of Grignard or 2 equivalents of organolithium, you make the ketone where the alkyl group that's added, it substitutes for the OH group, is the organolithium group. So actually both of these reactions are in the online quiz. Okay. But there were other reactions that were in the online quiz. Organolithium, again, same as Grignard, plus nitrile. We just saw the reaction of an H- with a nitrile. It was super messy. This one isn't going to be as messy. This one's going to actually be pretty straightforward. But what am I going to get? Here's what I'm going to get. Remember, whenever you react an organolithium or Grignard, there's always a then H plus H2O step. So what I'm going to make in this case is this. I'm going to make the ketone where I've replaced the nitrogen with the alkyl group of the Grignard or the organolithium. And you're probably going, where did that come from? Well, let's write the mechanism out. Can we understand this mechanism? We should. All right, so CN triple bond, forgot to say this before, carbon is delta plus, nitrogen is delta minus. What's the CH3 minus going to attack? The CH3 minus is going to come in and attack the carbon. Pair of electrons is going to go to the nitrogen. Just like the H minus came in, attacked the carbon, and the pair of electrons moved to the nitrogen. So I've added a methyl group here. I now have a double bond. I now have a nitrogen with 2 lone pairs, which means it has a negative charge. All right, that's great. We're done. Can't reform the CN triple bond because there's nothing to leave. All right, so now let's add H plus H2O to this. N minus gets the proton. What did I just make? I just made an amine. Or I'll put the shift base in quotes because this is actually what an amine is with the NH group. I just made the amine. Are amines stable? Yeah, no, they aren't. So what happens to them? Well, in the presence of the acid and the water, what am I going to do? Let's protonate the nitrogen. To form that species. You don't like that? Let's draw its resonance structure. Okay, what's going to happen next? Where's the water going to attack? Water is going to add to the carbocation. Don't like that resonance structure, okay? Water is going to come in, add to this carbon, pair of electrons goes to the nitrogen. What am I going to end up forming? Oxonium ion. What happens next? Lose the H plus. Now I'm starting to put in equilibrium arrows here. Okay, let's take a step back. So what did I do? I made the amine, and now I'm adding acid, and the acid and water that I added to form the amine is now going to react with the amine. Amines, we know, are unstable. So what happens? I'm going to protonate the nitrogen. The water is going to come in and add. What did I just make? I just made my hemiaminal. All right, I'm not done yet. I still have acid as a catalyst. What do you want to protonate? If I protonate the OH group, it reverses itself. Let's go ahead and protonate the nitrogen. What do I have? I've got an ammonium. What's going to happen next? I got my CH3 group over here. What's going to happen next? I'm going to lose the NH3. I now have that carbocation. Does that carbocation have a resonance structure? Yes. Move this pair of electrons here. I'm going to have to move that. Oh, sorry. Form a double bond to the oxygen. By taking that pair of electrons and forming the resonance structure. What is that? Let me make it a little bit clearer. What is that? It's a protonated ketone. Let's lose the proton. What did I just make? A ketone. I made that ketone. So if you react a Grignard with a nitrile, you end up forming the imine, which then when you add acid and water to it is unstable and reverts back to the ketone. Because how do I get from this ketone to this imine? I would react that with NH3. So what I'm doing is I'm reversing the process to form the ketone. Okay. So when you react a Grignard or an organolithium with a nitrile, you end up adding that alkyl group, but you end up making a ketone. So basically you replace the nitrogen with the alkyl group, but you end up with a ketone instead. Okay. So see, this is all kind of the same reaction, but slightly different sequencing. What else was in that quiz? What else was in that quiz was taking an acid chloride and doing a couple of things to the acid chloride. Number one, the acid chloride comes from a carboxylic acid. What reagent do I use to convert the carboxylic acid OH into a Cl? PCl3, SOCl2, not HCl. That will not work. So you can make your acid chloride using PCl3, SOCl2, any of those reagents, but not HCl. Okay, great. Let's talk about the reductions of both. If I react the carboxylic acid with lithium aluminum hydride, and then do a then H plus H2O step, I'm going to end up forming the primary alcohol. I'm not done showing you mechanisms yet, so I'm going to hold off on that mechanism until we get to carboxylic acid chapter 24. Because there is a truly magic step in that I don't want to fluff over. I've already used up all my magic in the first two reactions that we did. On the other hand, lithium aluminum hydride and then an H plus H2O step for an acid chloride also reduces down to a primary alcohol. That mechanism I can handle. Okay, remember lithium aluminum hydride has 4 H minuses. What's the H minus going to do? It's going to come in and add to the carbonyl. Great. Now what's going to happen? What's going to happen now is this O minus is going to try and bring its pair of electrons back down. It always tries to do that. But for the first time today, there's a group that can leave. The Cl. What did I just make? An aldehyde. Am I done? No. Because remember, LiAlH4 has 4 H minuses. So H minus number 2 comes in and attacks that carbon, and the pair of electrons goes up. So I add a second H. The O minus tries to bring the pair of electrons back down, but there's no leaving group. Carbon, hydrogen, do not leave. It's done. It hangs out and waits for acid and water. Final product, primary alcohol. That mechanism we can handle. Okay, so both carboxylic acids and acid chlorides with lithium aluminum hydride will form primary alcohols. Great. Except I'm back in chapter 22. Aldehydes and ketones. I want to make an aldehyde out of an acid chloride. I want to stop at the first H minus. Okay, lithium aluminum hydride. Remember, lithium aluminum hydride has 4 H minuses. Lithium aluminum hydride is a very strong reducer. It took the aldehyde down to the primary alcohol. I need a hydride. I need a reagent that has uno hydride, that just has one hydride, and it's a lot less powerful. Right. What you do is you do this. You put on one hydride, and you replace the other 3 with tertiary butoxides. So you still have 4 negative charges attached to the aluminum, but 3 of them are tertiary butoxides. Now I have 1 H minus, and I have a reagent that's a lot less reducing. My H minus does what? Comes in, attacks the carbonyl. I end up forming my O minus with my Cl. Again, O minus brings a pair of electrons down because it can kick the chlorine off. I form my aldehyde. There's no more H minuses to add. And even if there was, this reagent is weak, so it cannot throw a second H minus at the aldehyde. It stops. So this is a much more milder reducing reagent. And so it stops at the aldehyde. So with the lithium, it's called lithium tri-tertiary aluminum hydride. You end up just adding one hydrogen, and you end up replacing this chlorine with a hydrogen. It's a great way to make an aldehyde. The lithium aluminum hydride is too strong. Okay. Actually, as is sodium borohydride as well. All right, let's use that same approach to make ketones. So we say, great, acid chloride, methyl magnesium bromide, or methyl lithium. Now, if you remember back in this reaction, we always had 2 of these. And the reason is because the CH3 minus comes in, adds to the carbonyl. We end up forming the O minus with the Cl. We add a Grignard, our alkyl group. The O minus brings a pair of electrons down, kicks off the chlorine, and I form my ketone. Now, the problem with the Grignard or the organolithium reagent is they are very reactive. And so we always forget that we have like a bazillion of these molecules in solution. So what happens is that when the first Grignard or organolithium adds and forms the ketone, that a second one will be present. Even if there's one equivalent, you could say, well, one hasn't reacted yet, so the second methyl group will add, so that we'll end up with not adding one methyl group, but adding 2. So back in the Grignard chapter, we just said, you know what, we're going to add 2, and we're going to make the tertiary alcohol. O minus cannot bring the pair of electrons back down because there's nothing to leave. It waits for H plus H2O to come, and it forms a tertiary alcohol. Okay. Remember, this chapter, I'm back in chapter 22 now. I want to make that ketone. I don't want the tertiary alcohol. I want to stop here. All right, so now what I have to do is I have to go back and let's analyze the approach I used before. So when I was trying to make the aldehyde through reduction, I said, well, lithium aluminum hydride is just way too strong of a reducing reagent. It'll take the acid chloride and take it all the way down and add 2 H minuses. So I took the approach of, okay, let's use a milder reducing reagent that just adds 1 H minus. Is there a reagent that will be milder for a Grignard-like reaction? And believe it or not, there is, and believe it or not, we know what it is. Acid chloride plus lithium cuprate. Lithium cuprates are the less reactive versions of a Grignard or an organolithium reagent. Just like lithium triterpsbutoxy aluminum hydride is the less reactive form of lithium aluminum hydride. So what happens here is I just add one CH3 minus the O minus brings the pair of electrons down and kicks off the chlorine. So now I form my ketone. And that's it. The cuprate is not able to add a second methyl group to the ketone. And so the reaction stops at the ketone. So if you want to make a ketone, then what you end up doing is you end up using the less reactive counterpart to a Grignard, which is our friend, the lithium cuprate. And we're going to see that again in our reactions. Okay. So those are the extra reactions that were in the quiz from last time that people only asked about after the quiz, after they turned in the quiz. Because if there's stuff on here you don't that you don't understand, you can always ask about it. But now these reagents these are the reagents that we're missing. So you have another opportunity for that quiz. You're going to have to input all of the answers again, sorry. But it will score and give you the highest of the two scores. So if you didn't know what was going on before, which, I mean, how would you have known what's going on before? Because I don't think this is in the textbook right now. It's in there later, and when it's in there later, we'll review it. But these are the reactions. So that quiz will be due on Monday. And so you can go ahead and redo that quiz and then resubmit it, and it'll give you the high score. Okay. So we're going to come back to amines in the next lecture, and we'll probably finish up the amine chapter in the next lecture, which will be for, and I hate to put dates on this stuff because then I can't use the video again, but it'll be the video for Monday's class period. We will pick back up in chapter 23 and maybe finish or come close to finishing the rest of the amines chapter. Okay.